Okay, in this tutorial, I want to dive a little deeper in Kangaroo, and we just do it this time with surfaces because a lot of time we can't work with meshes or it's limited. So we want to work and we want to see how we can use, for instance, certain subdivisions in the surfaces like a hexagonal grid as a way of using a Kangaroo for simulating mesh system or a spring system, let's call it. So we can use Launchbox hexagonal grid cell, which is basically a component inside the Launchbox. So we can use that to draw a series of cells, so hexagonal cells. So let's just do that. And I want to use this as a way that we can simulate some sort of relaxation, but we want to apply forces. So this become like an elastic mesh that it can relax itself and we can add different forces to it, but also attractor point. So for that, let's first bring the main engine, Kangaroo physics, in. And I want to use two different type of forces. One is U force, which is the vertical force that we saw it in the previous tutorial on mesh, Kangaroo on mesh. And we can also add a spring form lines, which add the spring factors to these lines. So let's see how we can do that. As we saw, we need the forces that basically it can be both of these forces together applied there by holding the shift, and they can be applied. There's anchor points. So what I want to do, I want to use the all around these points that we are seeing here as anchor points that this hexagonal mesh is going to be anchored from. So in order to access to all these points, what I can do is to get the curves around the surface and then find the intersection of that curves with all these hexagonal cells. This would give me all the contact points that the hexagonal cells are connected to the edge. That can be a good way to get to the anchor points. So let's first of all find how we can do that. So there is a command called curve intersection. Maybe I should not have a space in between them. So curve to curve, this one. And it asks you what are the first sets of curves. So you can say all my hexagonal curve. And what is the second curve? Basically, I want this rectangle around my surface. So for getting access to that, what I can do, I can just use brep edge. Let's see, brep edge. And this gives me all the edges that our initial surface has, including the curves around it. So this curve, if we get the intersection, let me just hide everything. If I get the intersection, you see that it's not working properly. And the reason is that I have to make sure this is grafted. Again, sometimes I myself don't know exactly when, but then when I see that it's not working properly, but I know that the result should work, it's because, for instance, the data structure is not properly structured. So you can graft it and you get access to all the points around, and you can use that points as an anchor points. It's always a good habit to flatten when you get to the Kangaroo engine to make sure that all the forces and anchor points are all flattened into one big data structure. And we want to add these two forces. So how can we do this? Let's start from the spring. A spring is basically, it shows the springiness of our mesh. So if we have all these cells and they have their centers, these cells, these are basically, if I bake it, you can see how it's structured. So there's literally a series of curves that they overlap with one another. So first of all, what we can do, we can say, we can use the lines as a connection points for our springiness, but then there are doubles. So in order to avoid that, we can use explode. So first of all, we explode all the hexagons. Sorry, this comes from our hexagons. We explode all our hexagons. And now I can just remove all the lines that they're double. This would give me, and you can flatten it, so you make sure that all the lines that they're double together, they're in one pocket, and then remove all of the doubles from the structure, from the data structure, and you can use that as your connection, right? And then it also asks you what is the stiffness and what is the damping and what is the rest length. Usually I just use the rest length. And what is the rest length is basically saying that to what length our object is gonna rest. It literally is saying that, meaning that if the length of, so if you calculate the length of each line, so if you calculate each line, and if you say that I want every line be the same, but subtract that, subtract the actual length from some number, so let's say 2.2, mean that measure all the distances for me, all the lengths of all the cells, and then just make it slightly smaller, so it's become really elastic. It wants to, basically the 2 points here and here wants to pull toward each other. This becomes the rest length, and if you add that to our force, then you need to also define what is the geometry that you want to basically insert, and for that let's just basically put our geometry as our curves. And I just want to quickly, let's see where we are at the timer, make sure that the intervals are 20. And if you rest it, let me hide everything else. Stop. And if I rest it, you can see that it's relaxing. So you can even make this really, actually make it bigger, make it really elastic. But this is not, maybe we add another, maybe and we add points in our surface, and we say that around our surface, according to the distance of these points, we add a vertical force. So for that, so let's add both springiness as well as the U force to work in sort of combination to one another. So let's see how we can do that. So for that, we can say, okay, get our points. This is our point. And let's say that we want to measure the points to all of our points in our cells. For doing that, we already removed the curves that we basically, they were doubled, not curves, the lines of our hexagon. So we already have the clean lines. So now if we just say that point on a curve, we say that, okay, just find the beginning. Let me just hide everything, including our kangaroo. Actually, let's keep the lines. If you say, okay, just get the beginning or end of these curves, you see, and use that as a point that our attractor points is going to insert a force. The reason that I want to do that is that I don't want to just add the force to entire system. You can obviously do that, but I want to make it more specific based on these attractor points. So let's say that just these parts of our mesh is being affected by vertical force, and the rest of the mesh has to sort of conform or adapt to that specific force. So in order to do that, we, similar to our attractor points, we just use pull points. These are all of our points, and this is our attractor point. So we have all the distances. And now we can say that just pick the points, just pick the, first of all, yeah, just, so we have all the distances. So let's say we want to say just pick the ones that they're closer to our attractor points. So let's say they're 30. So just pick those points that they're closer to our attractor points. So you can use the call pattern and use the smaller. So you have all the distances. You measure what is which points are closer than 4 or 5, and then you have all these points around here, right? And now you can say that, okay, now you have these points, and use those points as the point of the force, of the vertical force, but instead of just all of them being a certain number, I want to add the force according again to the distance to that center point. So for that, you can also use similar principles. So you can say the force is in the z direction, we know that. But I also want to say that the distances should come from a number from our distances. So you copy, let me just do this. You copy the call pattern. Instead of picking the points, this time you're picking the distances, and use that as a way that the force is being, so now you can see that it's closer, the vectors are smaller, the further out, they're bigger. So I want to make this the opposite. So if I just right click here, you can type -x. Let's see if that helps. -x is not helpful because it's just bringing the force downwards. It's not actually changing anything. But as I showed before, we have to remap these values. So you use remap. You say, okay, get all of our distances that we have, and find the bounds, what kind of range our numbers are, and then you have to reverse that. So for doing that, you have to deconstruct bounds or deconstruct domain. Oh, my timer is not happy, so I'm going to disable it. Okay, deconstruct the domain, and then use construct domain to reverse this direction. This number can be our value. Right now, you can already see that as it's closer, it's bigger, as it's further out, it's smaller. I'm gonna also multiply these numbers, it's a little bigger. Let's add that to our force as well, and make sure that both of them are flattened. And now let's turn everything off. Let's see if everything is working. Definitely not moving upwards. I think one of the reasons is probably is our points needs to be actually, in order to troubleshoot, let's just add a simple vertical point. I am suspicious that our points are doubled here because we are actually, we have to remove, I think we have to remove the points, but I'm not really sure. So let's just see if we add just the vertical force. Is it actually doing it? Oh, it is. So maybe it's just, it was the matter of, so let's bring this back. And I want to add a bigger slider here. Yes, it's working. So now you remember you can work with the rest length, you can change this value, and you can change the vertical force in order to see the different results. You can also notice that it is different and it's very local, right? So the force is starting from here. That's why you see the bulge here. And for now, let's make sure that we turn off, so you can make this to curves and turn this off so we can actually see what we're doing. We can already also see that if I change this, you can see that it's very specific to the location of our points. What I would like to do, I would like to internalize this and hide this. So let's see if I can in real time change this, because this would actually see some of them, but you need to actually restart so it doesn't show. But you can start thinking about ways that, for instance, how there would be another force that pushed this down from another direction. You can have attractor points that also change the rest length. So at the moment, our rest length is a number that it's the same for the entire grid. Is it's completely generic number, but you can think about ways that, for instance, attractor points can affect the rest length. You can also, so I'm going to pause this. Oops, sorry, I closed it accidentally. You can also think about ways that, for instance, this can be mapped to your mask. So let me see how, for instance, apologies for so many surfaces here, but yeah, so for instance, you can use this as saying that map our curves, so map to surface, use these curves, map it based on it asks for the source surface. You can say, okay, my source surface is this, the initial surface that you have, and it asks you, what is your target surface? Your target surface, for instance, is the surface that you made for your mask, and use that, yeah. And then if you do that, not only you see the simulation there, but you have to see the simulation here too. You see that it's going inside. So I can just select the mask and flip the direction of the surface. If you do that, then you should move outside. And you can think about ways that you can, for instance, simulate maybe breathing. Anyway, so you can think about ways that the forces from the face or from the body can change the forces that it can be applied to this mesh. But more than anything, I wanted to show how you can use the Kangaroo on a flat surface and then similarly simulate that on your original mask. Yeah, that's pretty much it.